Hey calculus students, this video is going to be on what's called the first derivative test for finding extrema. It's going to be, what we're going to kind of move into is doing stuff with equations that is related to what we've been doing with graphs. So we're kind of like taking all of our understanding about how derivatives relate to the function graphs. We're using that to think about equations and still finding maximums and minimums, but from equations. So first of all, I just want to do a little vocabulary review of the word extrema is unfamiliar for some people. So the idea of an extrema are these are the maximum and minimum values of a function. So extrema just kind of corresponds to like extreme values. So maximum and minimum values of a function. And these are y values, not x values. So we'll think about like at what x values does an extrema occur. And I just want to kind of draw you a little picture of like all the different types of extrema that we have. So do your best that you can to mimic my picture. I'm putting points at specific heights, so try to kind of like relative to each other, try to make your points height-wise match my points in the sense that like this point is below that point and this point is above this point, okay? So once you kind of have that sketched out, we're going to kind of draw an x and y axis. We're going to kind of use all these different points to think about all the different types of extrema we can have. And so we've been hearing the words like absolute extrema, absolute min or max, local min or max, relative min or max. So I kind of want to give you a picture that to kind of place all these words on. So first of all, we think about absolute extrema as being like on the whole interval where a function is defined, where is the absolutely highest and lowest y values. So like we would say this point up here looks like an absolute maximum, and another word that's used interchangeably with absolute is going to be global. And the idea of global means that global is like considering the entire domain. Okay, so it's like if we think about global meaning like the whole world, in the world of this function, the whole world is the whole domain. So then the absolute minimum looks like it occurs down at this endpoint. So this would be the absolute or global min. And then there's these three other points. And these end up being local or relative maxes and mins. Because relative to the points around them, they are a highest or a lowest point. So I think we'll start over here where we come to a peak. This it looks like if we kind of like ignore everything else, if I just kind of focus in on what's local, this is the highest point compared to the points around it. So we call this a relative, or relative to the points around it, or local maximum. Similarly, this would be a relative or local minimum. And lastly, this endpoint we still think of as a local minimum because if I kind of zoom in just around here, any point close to it is higher than it, right? So the key kind of understanding is that maxes and mins can happen at endpoints. Oh, local or relative minimum. Okay, so now I want to introduce to you another new vocabulary word, which is called a critical point. And I would argue we've already been identifying critical points graphically. A critical point is a point on the interior of the domain of a function So that just means, it's a lot of formal language, but it means it's not a point at either endpoint. It's not either of these like endpoints, but it's somewhere in between. At which one of the following things. So either there's two things that qualify as a critical point. The first one is that the derivative value is 0. And the second thing is that the derivative doesn't exist. Okay, and if we kind of like think about this definition compared with this picture, right? Places where f prime is 0, that's going to be like where we get to these like smooth peaks, right? So this where this local max is or this local min is, those are going to be places where I could draw a horizontal tangent, so the derivative value would be 0. And f prime not existing, that's where f of x is not differentiable. So that's like this little cusp that is right here, okay? And the key understanding is that if there's going to be a local max or min somewhere in between the endpoints, it's going to happen at one of these 2 points, right? Maxes or mins are, what we noticed before when we were like looking at graphs, is max and mins are always happening where the derivative is 0, but also where there's something like a corner or cusp. So we also are thinking about where f prime of x doesn't exist. So the big idea, like the big idea or takeaway here should be that critical points help us find maxes and mins. And we should keep that in mind as we move forward, okay? So now what we're going to get to is what the first derivative test actually says. So we have and when I write it, you're going to say, well, I already knew that. And it's true, you did already know this. So we're just kind of formalizing it and then seeing how it applies to equations. So the first derivative test says that once you've identified where the critical points are, so if we're looking at a critical point C, and we'll call it C, then we'll see a couple different things happen. The first thing that could happen is that the derivative changes from positive to negative. Okay, and we know visually we can think about what this looks like. If the derivative changes from positive to negative at some x value c, it must be that either we have something that looks like this, like something smooth, or maybe we have something not smooth at that point, so maybe we have like a cusp. Okay, but either way, here this gives us like f prime equals 0, and this would be f prime is undefined. But in both cases, we know we'll have a local max, right? That leads to a local maximum. And I would say, like, we can't say for sure right now if that's an absolute maximum. We're gonna start considering, like, how do we decide if it's local or absolute a little bit later in this unit. But for right now, we can say it's for sure a local maximum and maybe even an absolute maximum. So the next thing would be that f prime changes from negative to positive. So that looks like graphically, if its derivative value is 0 at that point, it's going to look like this. Well, and if it has like some sort of, it's not differentiable there, then it looks something, maybe it has like a V corner or something like that. And both of these cases are going to give us a local minimum. So there's one more thing that could happen though, and that would be that the derivative doesn't change sign. So what that would look like would be something like this. For here, there's like a place where f prime equals 0, but it's increasing on either side of that, so there's no max or min. Or you could also have something where the derivative is undefined and it still doesn't change sign, so that might look something like a vertical tangent would work. Oh, I didn't draw that so well. Okay. So there's a place right there where f prime is undefined, but this is not a max or min. So the idea is if the sign of f prime doesn't change, we don't have any extrema at that point. Okay, so now we're going to see how can we put this into action given an equation. I'm going to do a couple of examples. So we'll say find the local extrema of f of x equals x to the third minus 3x squared minus 9x. So step 1 here is take the derivative, right? So the idea is like of the first derivative test, it says, well, if we know where the derivative is at a critical point, then if we know what the critical points are, we're able to see where the maxes and mins are. So it is we need to find the critical points. So we're going to say find f prime and critical points. So this takes us back to our derivative rules. So for f of x here is x to the third minus 3x squared minus 9x. Taking the derivative of that, I get 3x squared minus 6x minus 9. And if I want to know critical points, I want to know where this thing is undefined or 0. Well, this thing is a quadratic, so it's always defined. So I just have to worry about where is it 0. If I set it equal to 0, then I can solve this algebraically. I just need a factor. So I can factor out a 3, 2x minus 3. Then this is a quadratic that factors, so it becomes x minus 3, x plus 1, 3 out front. And then remember, since this is equal to 0, I can just set each factor equal to 0, so I get x equals 3 and x equals negative 1. Okay? So that's step 1. Now I know these are my critical points. And for polynomials, we'll never really need to think about where the derivative isn't 0, or sorry, where the derivative is undefined. For right now, we're just thinking about where is the derivative 0, and eventually we'll look at things where the derivative could be undefined. So my step 2 now is we're going to create a number line to kind of organize the critical values. So I'm going to draw a number line, and on that number line I'm putting 3 and negative 1. And those are kind of like my changing over points. So I'd like to think about what's going on either side. So the idea is like I need to know if at negative 1 am I changing from like positive to negative to positive, or maybe there's no sign change at all. So I'd like to think about like what is f prime doing here. So for something less than negative 1, like if I plug in negative 2, say, into my derivative function, I'd like to know, will it be positive or negative? So I'm going to say plug in negative 2 for x. So here, I'm just going to plug it into the factored form. So like negative 2 minus 3 is still negative. So I have something negative times negative 2 plus 1 is still negative. So I'll get like positive 3 times negative. That's going to give me something positive, right? So then, same idea in the next interval, I could plug in something between negative 1 and 3. Well, if 0 is in there, might as well plug in 0 because that's the easiest thing. So let's say I plug in x equals 0. Then in my first factor, I'm going to get something negative. And in my second one, I'm going to get something positive. So negative times positive gives me negative. And then lastly, you need to plug in something above 3. So let's say 4. If I'm plugging 4 here, I get something positive, positive. So everything's positive. This is going to be positive. So now, what does this tell me about what's happening at -1 and 3? I now know, and like you could memorize, well, positive to negative, I know maximum. The other way of doing it would be to do it more visually, which is to say, like, draw a little picture. Sorry, ignore that little dot. So this is my function f. So when f prime is positive, I know f is increasing. Negative, I know decreasing. Positive, increasing again. And now I can kind of visualize that increasing to decreasing, what's going to happen right here is there's going to be a max. What's going to happen right here, I'm going to have a minimum. And I think, like, if you kind of visualize, oh, up to down, you'll see the max, and down to up, you'll see the minimum. Okay? So the last step is to draw your conclusions. So I would just say f of x has a local maximum at x equals -1 and a local minimum at x equals 3. And now I'm done. Okay, so for the sake of time, and I'm trying to not make these videos quite as long as they've been in the past, I'm just going to give you all a u-try problem, so see if you can repeat this process with the function. So we're going to say find local extrema for f of x equals 3x to the 5th minus 5x squared. Okay, so you're going to take its derivative, set it equal to 0, find those critical points, and create the number line. And we'll be discussing this in class.